This is the Cauchy-Euler problem we were working on last time. I think we got as far as the finding W1 or something like that. So this might be a little bit easier to read than my my little scribble notes. And hopefully I did everything correct there. All right, so let's go through this problem. The first part is finding the solutions to the homogeneous differential equation. And so we found that. I think we got x is equal to, or m is equal to -1 and -1/2. And we got these rational functions here. Rational function, the square root, rational function. And we found the Wronskian. And the Wronskian turned out to be, after you do this multiplication, you get just one term. And you get 1/2 x to the -5/2 power. And we had to do this step over here to try to make it in a form that would fit our formulas, which is to say it has to be in a normal form. So the coefficient of the x, or the y squared, or no, coefficient of the y double prime had to be equal to 1, so we had to divide out by 2x squared. So when we do that, our right-hand side significantly changes. So that change can be seen in a variety of ways. We can keep it as two separate fractions. I think that's how we started to do it in our class. But here I decided to just combine it into one fraction because maybe it'll be easier. All right, so that's your f of x, or g of x, or whatever they call it in the book. That's going to be the function on the right-hand side of your normalized differential equation. And that's what you're going to use for W1 and W2. So this is where I started to do it in columns. So the one column, the left column would be the W1, the U1 prime, the U1, and then the U1 times Y1. And then the second column here, the right column, would be the W2. So this is what I ended up getting for W1. W1 is going to be negative x to the -1/2 times this f of x, or g of x. And then we divide out by the Wronskian, and then we get U1 prime, and this thing simplified to a nice polynomial, it turned out. So we have the polynomial, that's U1 prime, and so this would be an easy step to take the integral of that to get U1. And so we got U1, and we multiply that by Y1, and then we got one part of our Y particular, Y sub P. Okay? So I think that this is as far as we got in our notes from last time. So here's the rest of it. The W2 would be the same as the Wronskian, except the second column would be changed. And then it looks like I get x to the -1 times that f of x function. I divide out by the W, the Wronskian, and then I get this expression over here, which after you simplify it looks like not quite a polynomial, but it's still a couple of power functions that's going to be easy to integrate. So we take that and integrate it, and yeah, just have to be careful the fractions. You add 1 to the power, and so when you add 1 to the fractions, you have to make sure that you add the fractions correctly, and then you divide by that, which is the same thing as multiplying by its reciprocal. So this is what I ended up getting for U2. And then I take U2 and I multiply it by Y2, and then I get another nice polynomial similar to the other polynomial that we looked at. So the particular solution is going to be the sum of the u1 times y1, and then the sum add that to u2 y2. And since they're both polynomials with the same degrees and same terms, we just combine like terms, and then we get this. Okay. And then the general solution would be the linear combination of the homogeneous differential, or the solutions to the homogeneous differential equation, plus the y particular that we just found. Okay? So this is available in your notes already. It was online yesterday, and you can just the Wronskian business is to find yp. Yeah. And yp is just this business over here. This stuff comes from the first part where we found y1 and y2. Okay? Any questions? So we also did a couple days ago, or a couple of lectures ago, we had an extra problem for this as well. So I think we kind of went over this already, but I just want to show you. Somebody emailed me about this thing not being available. So it's already here. So this is similar to what we just did. Yeah, so it's up here already. Okay? Yeah?
So, like to solve these, so for the right side, you can use the Wronskian or the coefficient thing. And for the left side, you can use the quadratic formula or the y equals x to the m power.
Yeah, well, it depends. It depends on what you have, right? If in this problem, I keep downloading it. There it goes.
You can combine them, like switch them up to each side.
We're not combining them. See, so this thing, when you say the quadratic formula, you're really solving for the fundamental solutions. So we should kind of keep that idea separate from solving for homogeneous. So in this particular scenario, we had our g of x looks like a polynomial, but when you really divide it through, where is it? Yeah, when you really divide it out, our g of x is not a polynomial, it's a rational function. So we definitely want to use variation of parameters for the Wronskian. The other problem that we did also used the Wronskian. Oh, here, we could have used undetermined coefficients for this, which is to say that my solution would look like ax plus b, and then you solve for a and b. That probably would have been a lot easier than doing this business, but we decided to do it this way. Okay. Any other questions? All right, so we've been dealing with these things and getting general solutions for them. And we haven't incorporated the idea of an initial condition. And so when you have initial conditions, when you're dealing with differential equations with constant coefficients, I think finding the initial conditions is pretty straightforward. And it probably would be too if it's not. So this is not a differential equation it's not a linear differential equation with constant coefficients because the coefficients are not constant. And so in those cases, the idea of an initial value is a little bit trickier. So let's take a look at a little bit of the theory behind the initial value and an approach to try to solve for these types of differential equations. All right. So I was debating whether or not to go over this section, but I think we're going to go over this section. What's the next section? 8? I suppose I have it in my notes. Yep. So we're going to introduce a tool for us to try to solve for initial value problems, higher order initial value problems, and we have to get through a little bit of some preliminary work before we get to do some examples, but it's all kind of related to the variation of parameters after we see things kind of cleared up. So this is our differential equation, and its differential equation will have initial conditions. And for now, let's take a look at just a second order differential equation. And we know that our solution is going to be, by the superposition principle, our solution is just going to be the solution for they call it y sub h. They call it y sub h or y sub c. I forgot what they called it. So it turns out that if you don't have initial conditions, then your solution is just going to be a general solution with a C1 and C2. But if you do have initial conditions, you would need to solve for the C1 and C2, and we'll see that y sub h is going to be the solution to the differential equation, the homogeneous differential equation with the non-homogeneous initial conditions. That's y sub h. And then y sub p, the particular solution, will end up being the solution to this differential equation, the non-homogeneous differential equation with initial conditions at 0. So that's how we have to deal with these initial conditions. So we could do them separately, or we could take advantage of variation of parameters and put them together. So how are we going to do that? Let's see. And just copy everything and paste it on. Maybe I'll stop here for a minute. So to try to solve for this, what we're going to do is we're going to take a look at the particular solution. And remember, the particular solution was that u1, y1, and u2, y2. And if we take a look at where the u2 or where the u1 prime and the u2 prime came from, let's go back to the previous page to see where it came from. It looks like it's a mess. I think it might be easier to take a look at the notes that I typed up. So u1 prime comes from w1 divided by w, right? And w1, when you do these w1 and w2, when you do these determinants, we know that one of the corners, one of the slots in the top row is 0. So you're kind of guaranteed that when you do the determinant, either the diagonal or the wing is going to be equal to 0. So if you look at this, it's just going to be 0 times whatever this thing is, and then minus the function that sits in this lower left-hand corner is f of x. And then the function that sits on this upper is going to be y2. Right? So from the Wronskian, you have y1 and y2 on the top. When you modify the Wronskian to y1, you have 0 and y2 on top. So the determinant of that is f of x times y2 with a negative sign. So f of x times y2 with a negative sign, and then you divide by w, the Wronskian. Similarly for y2, or for u2, or u2 prime, for u2 prime, we have y1 and then 0 over here on the top row, and then we have the derivative of y1 and then the f of x function. So what does this turn out to be? This turns out to be just y1 times f of x minus 0, so we just ignore that. So that's y1 times f of x. That's for the w2 part, and then you divide that by the Wronskian, and that's how you get the u1 prime or u2 prime. Okay, so you see where these expressions came from? These just came from the w1 and w2 from the variation of parameters. So now, what they do here is they kind of put this together . And normally we would have like an indefinite integral here. But since we're looking at initial conditions, we can take a look at this as if it was a definite integral. And our independent variable result should be x. So we're going to go from the initial condition, x value, to some random value of x. So x naught is a specific constant value, and then x is still your variable. So that means if I use that as if I use my variable as my upper limit, I need a different dummy variable for my integral. And so here's p. So to find u1, I would take u1 prime and take the integral of that, and then I would evaluate it from x sub 0 to x. And then after I get that, I multiply it by y1 to get my u2. I would take the antiderivative of u2 prime and then multiply it by y2, and then if I add those together, I get my particular solution. So by doing this, you're actually also coming up with arbitrary constants C1 and C2. You're actually solving for C1 and C2 along the way here. Okay, so what they decided to do is put this together into one big integral and define a function that's inside. And so this is how they define Green's function. So they define Green's function to be this g of x and t So remember that x is the variable that we come up with at the end, and t is a dummy variable that we're going to use within the integral. So it's going to be, they just switched the order. And so the x's and t's are important where they're placed here, because when we integrate, we're going to integrate with respect to t. And then if you just multiply this by f of t, you can get your solution. Wow. A lot of stuff. Okay. So this kind of saves us the trouble of having to do the matrices, because the matrices are done for us already. If we just use this formula, and you're skipping a lot of steps. I suppose we should try it, see if it works. Let's try number 19 first. Well, I don't know why this starts at 19. All right. Let's just dive in, I guess, huh? So to find our fundamental solution, y1 and y2, we first need to consider the homogeneous differential equation and then solve for this. So we get m squared minus 4 is equal to 0, m is equal to plus and minus 2. So our solutions, y1 is going to be e to the negative 2x, and y2 is going to be e to the positive 2x. I just flew right through. Got it? You can almost see the solutions, right? Without actually doing the m squared minus 4. If you can't, just make sure you show your steps in your own notes. All right, now we can identify our f of x. It is already in normal form, so f of x is going to be e to the, yeah. Oh no, because it's not a repeating. It's not, it's one's positive 2, one's negative 2, so those are different. If they were both 2, then it would be, yeah, x e to the 2x. All right, we do need the Wronskian for our Greens theorem, so let's figure out our Wronskian. And because this turns out to be a nice couple of functions, you'll see the Wronskian should look f of x is e to the 2x, correct? So Wronskian is e to the negative 2x, e to the 2x, and derivative is negative 2e to the negative 2x and positive 2e to the 2x. So when we multiply it, e to the negative 2x times e to the positive 2x is what? E to the 0, which is 1. So I have a 2 minus negative 2, and just turned out to be 4. Okay? So that's always nice when we have a constant Wronskian. So now let's try to identify Greens theorem, or Greens function. I'm going to keep saying Greens theorem, but it's Greens function. So let's identify Greens function. Greens function is g of two variables x and t. You guys have it memorized already? It's something with a y1 and y2, right? All right, so if we look at it, it's y1 and y2, and the other one's y1 and y2. You just have to know where the x and the y belong, right? And the order is going to matter because there's a negative, there's making the difference here, so the order is going to matter. So y1, y2, y1, y2, except y1 is with t on the first one, and then it's with the x on the second one. And then y2 is with the x in the first one and t the second one. And the Wronskian has to be a function of t because that's going to be part of u1 prime, and so that needs to also be integrated. Okay. It might, I don't know if it's easier to remember, but if you remember this to be the first term instead of the second term, when you do the W1 determinant, that W1 determinant always comes up with a negative sign because of the determinant. If you want to try, and then so that's y1 is a function of x. But I don't know, that might be more confusing than it's worth. And it's not like you have to remember this formula anyways, because you'll write it down in your sheet of notes. And
Yeah.
When we integrate, we're going to integrate with respect to t, and then it'll become x. Yeah. And then there's an x naught, which is going to be the starting point in your initial condition. Yeah, it's around Halloween time. I don't think it's before or after Halloween. It's before, yeah. I hope so. Well, I mean, I'm just going to take my old exam, I guess, and just...
So are you going to do that next week?
Sure. I might even do it this weekend. Oh, wow. If I remember, if somebody emails me, I'm going to get 15 emails. Are we close to this?
I mean, it works though.
What?
If you have to set a reminder for yourself, you just tell everybody to remind you.
Yeah. Okay. Email me this weekend. I'll get the test out. Where are we? We are, okay, Y1. So the nice thing about this particular problem is the Wronskian's constant. You're not always going to have that luxury, but since this is the first problem in the set of homeworks, turns out to be nice and easy. But normally, if your Wronskian is not just a constant, you have to make sure that whatever x value you might have had here, you change it into t, because you're going to integrate that with respect to t. All right, the rest of the stuff, we got a y1, so that's e to the minus 2, and the y1 has a t for the first one. And then y2 is e to the 2x. y2 is going to be a function of x for the first one. And then the subtraction sign, and then we got y1 as a function of x. So that's e to the negative 2x, and then e to the positive 2t. And that's your Greens function. All we have to do is integrate that. Oh, no, we have to integrate that and then multiply by f of t. Say it again? I think according to this, Greens function is kind of devoid of f of t. There's no f of t here, and they do the f of t in the integral. Oh, but f of t was kind of built in. Yeah, so this f of t that was part of the determinant was factored out. We might have not seen that, but this f of t was factored out, and then it goes when you're integrating it. That's where you use it. And the thing about this is, and the reason why they do this is that they figure if you have a set of differential equations that you're solving for with the same left-hand side, and then the f of t changes from 0 to e to the x to sine x or whatever else it changes to, then all you have to do is make this one small change from your Greens function, which is not really part of Greens function, but when you integrate Greens function, you just put a different factor to integrate. So that's the reason why they kept Greens function without the f of t. Okay, so we were, let's clear out all the scribble. Although circling the f of t here might be good to see. So that was factored out of Greens function. All right, so back to our problem. Our solution then, y, should equal to, I call it yp, but I think it's going to be everything. Oh, let's see. The solution is going to be the integral of g of x t times f of t dt, where t values go from x naught to the variable x. X naught is equal to 0, your limits are going to go from 0 to x. Because the lower bound is 0, and that's the x naught as the initial condition, comes from the initial condition. And the upper limit is going to be x. That's going to be the variable that we want to get at the end. And that's the whole reason why we introduced this dummy variable t. Because we don't want to integrate with respect to x and then evaluate it at x. That's confusing. So we integrate with respect to t and then put into x. We've done this kind of stuff before in Calc 2, where we define an integral function or something like that. All right, we have e to the minus 2t e to the 2x minus e to the negative 2x e to the 2t over 4 times e to the f of x, but evaluated at t, so e to the 2t. So I might be interested in breaking this up into separate parts. There's a 4 in the denominator that's a constant that I can take all the way out, and then I can distribute the e to the 2t. So let's, oh yes, 0 to x. So let's take the 1/4 out and then distribute the e to the 2t. When we do that, we're going to get 1 times e to the 2x, which is constant with respect to t, minus e to the negative 2x times e to the 4t. And then we integrate with respect to t, treating things with an x as if they were constant. So we're going to go to 1/4, and then I have e to the 2x times t, right? Because it's a constant with respect to t. And then minus e to the negative 2x, and then the antiderivative of e to the 4t, it's 1/4 e to the 4t. And then you have to go ahead and put in the 0 in for t and the x in for t. So let's see, we got 1/4, put in the x, so this is going to be x e to the 2x minus, put in the 1, this is e to the negative 2x oh, okay. All right, I think I successfully put in the x in there. Maybe I'll keep the 1/4 out for now. And then I put 0 in for t, and so the first one is going to be 0 because there's a t in there, and then 0 in for t, I'll keep the 1/4, and then e to the minus 2x. So now after I evaluated this definite integral, I don't have any more of my dummy variable. So the dummy variable, the dummy variable is gone. Okay. Be my much neater if I just typed it all up. Yeah. You don't have to agree. All right, so we probably can simplify just a few more things. Let's see, we're going to go ahead and do this 1/4 x e to the 2x. And here, a 1/4 and 1/4, that's 1/16. And then e to the negative 2x, e to the positive 4x should give me e to the 2x positive. And then when negative, negative is a positive, and then the 1/4 and the 1/4 is 1/16 again, e to the negative 2x. I think that's it. I hope it's right. Do you guys study hyperbolic functions? No. That's the section that they always skip in calculus. Figured out, you guys go to physics, you'll learn it. What? Yeah. I suppose we should check if this is right? I mean, so let's go to Wolfram. Did you know that Wolfram can do differential equations? Maybe I shouldn't tell you. So the command for solving differential equations is called dsolve. Or do you guys watch the episode of Big Bang Theory when they're going to do an app on the phone? They take a picture of a differential equation and then they're going to solve it. No. I saw it, and I've been trying to get the clip on YouTube, and I can't find it. And I don't know which episode it was or what year it was, but they did it. I mean, they didn't do it. I don't know if such an app exists. So I don't know. I'm going to use the mathematical language. And so y, the second derivative of y, so y with a couple of apostrophes, is a function of x. So they need to know what they're solving for and what the independent variable is. And you can't use your phone on the test, just so you know, right? Yeah. I do have Wolfram Alpha on my on my phone, just in case I need to do differential equations. So it's equal to the exponential function of 2x. So it sees a differential equation, and if you have initial conditions, you would include the initial conditions. Actually, you would need curly brackets to include the initial conditions. So the initial conditions are y of 0 is equal to 1, y prime of 0 is equal to -4 in this case. So this is the initial value problem, and then you have to specify what you're solving for and what the variable is. Now what? Maybe it doesn't work. Didn't use our initial conditions. What's wrong with our initial conditions? Well, I don't know what happened. Oh, we see the 1/4 x e to the 2x at least. But the C1 and C2, according to what we got, it's 1/16, negative 1/16 and positive 1/16. I don't know why they didn't show the. Oh well, that's close enough. Yeah.
So if you plug in the 0 in there, should be 1 according to the initial. Is that what it's saying?
Yeah. Does it? It doesn't equal 1, huh? Because this is positive, negative. Well. Oh, you know what? We missed something. Y prime of 0 is what? Oh yeah, we didn't use that either. Well, the thing about that is that I thought this was already the whole thing. Let's see what the theorem says. Oh yeah, so maybe we have to solve for y sub h. Maybe we should have done that in the beginning. One. So y sub h is supposed to be the solution . It's supposed to be the solution to this thing when this thing is equal to 0. So we got y1 and y2, right? What's y1 and y2? Y1 is equal to e to the negative 2x. Y2 equals e to the positive 2x. And so YH is equal to C1 e to the negative 2x plus C2 e to the positive 2x. And so we want to use these initial conditions for that. YH prime, the derivative is negative 2C1 e to the negative 2x plus 2C2 e to the negative or positive 2x. So using the initial conditions, we have we put 0 in. E to the 0 is just 1. C1 plus C2 is equal to 1, and negative 2C1 plus 2C2 is equal to negative 4. So how do we solve for that? I think if we just multiply the top by 2, so 2C1 plus 2C2 is equal to 2. Negative 2C1 plus 2C2 is equal to negative 4. So this is gone. This is 4C2 equals negative 2. C2 is equal to negative 1/2. So C1 is going to equal to what? 3/2? So we go, so y sub h is going to be 3/2 e to the minus 2x minus 1/2 e to the positive 2x. So we add that to the y sub p. So we get 3/2 e to the minus 2x minus 1/2 e to the 2x plus y sub p that we just found earlier, 1/4 x e to the 2x minus 1/16 e to the, that's a negative, that's positive, 2x plus 1/16 e to the negative 2x. So I suppose if we simplify that, we're going to get, let's put this one first, 1/4 x e to the 2x. And so the positive ones, 8, 9, negative 9/16. And then they're both positive times 8. 3 times 8 is 24, plus 1 is 25. 25. So if we, Randall, if we put 0 in, like you were saying, is this going to equal a 1? I hope. The first one is 0. This is negative 9/16, 25. 25 minus 9, 16 over 16. Yeah, whew, works. At least that one works. We need to check the other one. Okay. Say it again. Yeah, so if x is equal to 0, we were just checking the first one, if our solution. Wow. Any questions? Of course, you're just gonna print out the notes and look at them and understand them. I'd like to do another one, but you know, this one took us like 45 minutes, so I'll start it. What? A trig? All right.
Like when we see it on the test, we're like, I don't know. Yeah, it's like easy class.
Let's do. Let's do number 23. Oh, cosine, cotangent. You guys know your trig? I got a calculator. Let's go. All right. Let's do it. All right, let's see if we can fly through this. We might as well try to find our y sub h from the beginning, right? Let's see if we could do that. So the homogeneous portion of the things is, if you do this in your head, it's m squared plus 1. So we have plus and minus I, imaginary number. So this will be sine and cosine. Are we done with that? Yeah. All right. So y1 equals cosine x, y2 equals sine x. Okay, for the homogeneous portion of things. And since we're here, I don't know why this is red. I usually save my red for last. While we're here, we might as well solve for y sub h. Y sub h is going to be c1 cosine x plus c2 sine x. And we'll take the derivative because we're going to need the derivative. Derivative of cosine is negative sine. Derivative of sine is positive cosine. And then we're going to need to put in pi over 2. Our x naught is pi over 2. So cosine of pi over 2, is that 0 or 1? So c1 times 0, and sine of pi over 2 must be 1 then. And then sine of pi over 2 is 1. And cosine of pi over 2 is 0. So it looks like C1, C2 equals negative pi over 2, and C1 is equal to positive 1. All right. So we got the homogeneous. Now we do the Greens theorem. So g of xt is going to equal to, remember, it's y1 with a t. So it's cosine t sine x minus cosine x sine t. Oh, we need the Wronskian. The Wronskian's 1. Right? Sine, cosine. Yeah. Note, note, note. This should be in a different color already. Note, Wronskian is 1. So I have my Greens function, and I want to multiply a Greens function by the f of t. It looks like it's a combination of cosecant and cotangent. So we have the integral, or y sub p, is going to be the integral from pi over 2 to x of cosine t sine x minus cosine x sine t times our f function. So cosecant is 1 over sine. I'll put cosecant t for now and cotangent t. So divided by 1, the Wronskian, so that just doesn't factor in. So it looks like we can distribute. If you remember your trig, what do you mean if you remember? You should remember your trig. 1 over sine and cosine over sine gets distributed. So we're going to get integral from pi over 2 to x. We got cosine t. I'm going to put the sine x first, since I can factor that x outside, which I didn't do yet, but I have cosine t times cosecant t cotangent t minus cosine x sine t, and then cosecant t cotangent t. So we're integrating from pi over 2 to x. So we got sine squared in the bottom and cosine squared on top. Oops, let me take out the sine x, because that's not really part of it. We're not integrating the sine because it's a function of x. Pi over 2 to x. We have this put together is a cosine squared t over sine squared t, which we'll figure out how to integrate in a second. Cosine x from pi over 2 to x. And then we have a sine and cosecant will cancel each other out, and we just have a cotangent. So that's a cosine t over sine t dt. We could do u substitution, or if you just remember the formula, it's something with an ln. So this is a thing. I would probably want to split up the cosine into 1 minus sine squared, so that I can split that up. It's 1 over sine squared. 1 over sine squared is cosecant squared t minus, and then sine squared over sine squared is just 1. And then I can integrate cosecant squared t. Over here, we do a u substitution. U is equal to sine, and then derivative sine is cosine. So it's just ln sine t. And we have to integrate that from pi over 2 to x. So sine x, the antiderivative of cosecant x is negative cotangent. Yeah, sure. Negative cotangent x minus, this is just going to be, this is a t, because we still have to put in those values, and then this is a t. And then here we can already evaluate, so this is cosine x ln of sine x, and pi over 2, sine of pi over 2 is 1, right? And ln of 1 is 0. So that goes away. So now we just need to put in sine x minus cotangent x minus x minus cotangent is cosine over sine. The cosine of pi over 2 is 0. And then that's pi over 2. And then we got the rest of this stuff here. And so we just distribute. We get cotangent is cosine over sine. Cosine over sine, so it's a negative cosine since the sines cancel, minus x sine x. Minus minus is a plus, pi over 2 sine x minus cosine x ln sine x. Can we combine anything? No. That's cool. And then we add this stuff that we found earlier, 1 and negative pi over 2. So our solution y is equal to positive 1 times cosine x minus pi over 2 times sine x. That's probably going to cancel with this, but and then plus the rest of this stuff. Two o'clock. Done. That was fun. You try it now.
Good job.